Welcome to another GL Communications product demonstration video. In this video, we will demonstrate how to measure one-way delay over a commercial 5G network using GL's Dual Utah HD hardware and the V-Quad software. Many mission-critical applications rely on fast data communications. Voice, video, and data quality will suffer if the one-way delay is too large. Measuring one-way delay is often difficult when the endpoints are in different geographic locations because each endpoint is relying on its own internal clock, which may not be synchronized. GL's solution relies on GPS to provide the accurate timestamping necessary to calculate one-way delay. This solution can be used to test any network, including 5G. In this demonstration, two cell phones will communicate over a 5G network. The cell phones are controlled by the Dual Utah HD via Bluetooth connections. The Dual Utah HD is controlled from a Windows 10 PC running the V-Quad software. This software allows the user to make and accept phone calls and transfer audio and digits. In order to conduct the one-way delay measurement, each Dual Utah HD is equipped with a GPS receiver. GPS is used to synchronize the send and receive audio pipes, and therefore calculate the one-way delay with millisecond accuracy. Please note that if the two cell phones are co-located, then they can both be connected to the same Dual Utah HD and V-Quad system. In this scenario, GPS is not needed because the one-way delay calculation is done based on the internal clock of the Dual Utah HD. First, we will connect the cell phones to the Dual Utah HDs via Bluetooth through the V-Quad software. Next, we will confirm that each V-Quad system is receiving the GPS signal from the GPS receivers. Then, we will set up a call and measure the one-way delay between the cell phones in an isolated lab network. Finally, we will repeat the one-way delay measurements on a commercial 5G network and compare the results. Here we are using Remote Desktop to log into two separate V-Quad systems on different PCs, each with a GPS receiver. We will connect an iPhone to the first system and a Samsung phone to the second system to perform a one-way delay test, first over the local wireless network and then over a commercial 5G network. Click Dual Utah Configuration to begin. Prior to connecting the cell phone to the Dual Utah HD via Bluetooth, set the sampling rate to 16,000, which is wideband audio. Under the General Settings tab, set the clock mode to GPS. The Clock Trigger Seconds option is used to synchronize the send and receive audio pipes. When the GPS hits the user-configured time, the Dual Utah HD hardware will open the send and receive audio pipes. It is based on the seconds digit in the GPS Coordinated Universal Time. The value can be set to any digit, but must be the same for both V-Quad systems. Under the Set Bluetooth tab, locate the device and click Connect. The phone connects successfully and the icon in the left-hand pane turns from white to pink. To ensure the GPS receiver is functioning correctly, click on the satellite icon. Under the GPS Status tab, you can view the longitude, latitude, and coordinated universal time. Green LEDs indicate that the receiver is working correctly. Also note that you can periodically sync the PC time to the GPS UTC time. Also note that 5 satellites are currently in use. Under the GPS Events tab, you can view the GPS NMEA messages in real time. Here we show the successful connection of the second cell phone to the second V-quad system. In order to measure one-way delay, we must first establish a call between the cell phones. Click Functions, Manual Call under both V-quad systems. Under one system, enter the phone number of the other phone and click Place Call. Then click Answer Call for the second system. Now the call is connected. Please note, you can also use scripts to automatically establish the call. We will discuss scripts later in this video. Now that the call is established, the cell phones can exchange files and calculate the one-way delay. Click Functions, Delay Correlation and Audio Analysis. Under the Correlation tab, check Enable Send Device. Make sure OWD is selected for the mode. Next, go to the Configuration tab and choose a correlation record time of 2 seconds. The correlation time is used to specify how long to send or record the audio file. 2 seconds is sufficient for a 5G network. However, if you are testing high latency networks such as satellite links, it is best to increase this number. The correlation factor is an accuracy factor of the recorded audio during the one-way delay test. 0.5 is considered acceptable. Repeat the same procedure for the second V-quad system. However, choose Enable Record Device instead of Send. On the receive side, click Start. Then click Start on the send side. Please note, the timers do not begin when the Start button is clicked. Instead, both sides will start their timers when the seconds digit of the GPS clock reads the preset value, which in this case was 3. Back on the receiver side, notice that it is now receiving audio. Now the test has finished. On the receive side, note the one-way delay result is printed to the screen in milliseconds. You can run these tests as many times as needed. However, make sure that both sides are started a few seconds before the GPS clock trigger. To record the one-way delay in the opposite direction, simply switch the Enable Send Device and Enable Record Device under each V-quad system. One of the most powerful features of the V-quad software is its ability to automate these tests through the use of simple scripts. Here we will show an example script. Click Open Script Editor to open an expanded view of the script. The script can control both the local V-quad system and the remote system by specifying the IP address of the remote V-quad system. If the two systems cannot communicate over a TCP connection, you can also run independent scripts on each side of the call, synchronized by time. In this script, we've configured the remote end to be the sender, and the local system to be the receiver. Click Start to start the script. The script view shows the specific line of the script being run in real time. At the bottom of the screen, under the Measurement Results tab, the one-way delay values are displayed. The Statistics tab shows additional details on the measurements. Please note, the VQuad systems can be configured to send the results to an optional central database with web browser-based access of the results using the GL Web Viewer. The Web Viewer is a convenient browser-based dashboard which displays the test results. Here we show the results from the one-way delay measurements by accessing the central database. Please note, the previous results were based in a lab environment on a local wireless network. Next, we will show the results obtained on a commercial 5G network. Here is a snapshot of one-way delay measurements taken on an actual NSA 5G network. As you can see, we observe one-way delay values of roughly 270 milliseconds, since NSA 5G networks do not employ voice-over new radio. Rather, the audio packets still traverse the 4G LTE network. In other words, the 5G network is underpinned by the 4G LTE core network known as the Evolved Packet Core, or EPC, and hence voice-over LTE. At the time of this video, no carriers in our area support standalone, or SA, 5G, which explains why the one-way delay over the voice network is over 200 milliseconds. There is also an additional 15 to 20 milliseconds of delay in the Bluetooth communication between the dual Utah HD and each cell phone, which can be seen as part of the results when we ran additional one-way delay tests on the same call using the wired headset cable. All VQuad and GL net test measurements can be displayed on Google Maps to show performance as a function of location during drive or walk testing. Thank you for watching. To learn more about our telecom testing solutions, please contact us. We look forward to hearing from you.